physical data and turning it into a digital format. Does that make sense? So that is the whole purpose of a sensor, is it takes something from the environment, some trigger, and it makes it to where it says, okay, this is my trigger, let's kind of roll with it. Alright, so they respond to physical stimuli. In other words, anything of their environment that they're supposed to be looking at, they can. Turns it into an electrical equivalent. And one of the things we use to do that is a transducer. So it converts one form of energy into another. So that's how we get a signal from a push button that turns it into an electrical signal. So what are some of the things that we look to sense? What do y'all think? Position, what else? Sound? What else? Speed is one, yeah. Light. Basically everything that you can sense about the world around you, we create sensors to do the same. Does that make sense? So position, speed, weight, counting it, pressure, flow rate, moisture, viscosity. This is all different things that you can test with. And the whole purpose of that testing is to verify it is under the parameters that you want it to be under. Does that make sense? So let's say speed. One of the things we look at with any manufacturing is what?
How fast it can manufacture.
Huh?
How fast it can be manufactured.
How fast? What do you know the real name for that is? Cycle time. Cycle time is a thing, and that is a big thing. Cycle time has a lot to do with efficiency, at the same time it doesn't. Because with cycle time, it's how long does it take me to get from a raw product to a finished product. That is my cycle time. And that is something companies track very harshly. Mainly because if you think someplace like Mercedes, how fast do they want to get a car out? Fast as possible. They don't manufacture anything. They assemble the cars. So they pull tier 1 manufacturing supplies from places like Gestamp, Broza, and everybody else around here. They all come together with those parts, and Mercedes assembles them. So they have a certain cycle time they want to keep up with. Okay? That is one of the biggest things in the field, is everybody wants you to hit that cycle time. Okay? So that's one of the big ones when you're measuring speed and you're measuring time, is how fast is this all going? Is it the way it needs to be? So one of the things we can use are switches and push buttons. So a push button is only there to take a signal, a physical signal, and turn it into a digital format. Say you push the button, here's what it does. Does that make sense? Same for a switch. It's all just what is the position of this, and it triggers something else. But this is actually a way of creating a sensor, because it's a push button. Just like a can't think right now. Just like a pressure switch, a push button can be set up to detect if something is there or not. All right. So there's a lot to be said about sensors. They can be digital or analog. What is digital? We talked about this a little bit before. What is Very close. Digital is all about the ones and zeros. It's either a yes or a no signal. It varies. So if you remember the old physical meters that had the little needle valve, the little needle that ran back and forth, that's analog. Digital is taking everything and putting into a 1 and 0 format, and it goes from there. Does that make sense? So to do presence, we have limit switches. Limit switches are physical switches that are, every time something hits it, it says there's something here. They're generally a contact. Huh? Exactly, we used it in pneumatics. It was the roller lever. That is a limit switch. But we also had proximity switches, which I don't know if we've really got around to really talking about those, but those were the rings that clamped on the cylinder. That's a proximity switch. It's non-contact, still does the job of a sensing presence. It just does it a little differently. Don't know?
We had like a proximity switch. It won't sense its fixes, like it senses the metal.
Yep. Well, I mean, it can sense a lot of different things depending upon the type it is. So we have things like inductive and capacitive, and those definitely rely on magnetics of some sort or a magnetic field. And we'll go into all of this a little bit more deeply here in a minute. So a lot of sensors are non-contact. Why? Why would we not want a physical contact all the time? Wears it out. Think about it this way. Your doorbell. How many times can you use the doorbell before it starts to break down? It lasts a long time, but eventually it breaks down. Because it's a physical thing. You're actually going up and having to press the button. Or take a look at your key fob whenever it's 10 years old. Right? What's going to eventually happen? Or your remote control. Well, not just the battery dying. What happens to your remote control for your TV over time? Starts to get stuck, starts to not work. So physical sensors they're still used quite frequently, but we also have a lot of different non-contact because then you don't have to worry about something hitting it. And it gets stuck and it gums up. Okay? So with non-contacts, we look at things like force, pressure, flow, speed, and temperature. These are all things we might want to do remotely, right? Especially when it comes to temperature. One of the coolest things out there is something like the lines of a gas kiln, where they're having to keep glass continually melted. However, the temperature of melted glass is something I think like 1,000 degrees Fahrenheit. So do you really want to be up on this trying to check temperature? No. So what do? You put in something like a thermocouple that sits there and says, oh, here is the temperature. And then we have position, so things like potentiometers, which we talked about in intro. What does a potentiometer do? First of all, what is a potentiometer, I guess I should say? It controls what now? Yep. Controls voltage. With a potentiometer, one of the things I've heard it called is a variable speed controller. That's what a lot of people seem to know it as. Variable speed controller is another word for this, but the true name is a potentiometer. I don't know how y'all remember the old style radios and the old style TVs, how they can only click so much far over before it stopped, and then you had to play the back on the other way. Same thing with a pot. It only goes so far around, doesn't do a 360. But its position allows for you to, how to say this? So the position is what allows you to, the knob that controls the position allows you to control your circuit. Put it that way. And we'll talk about encoders and all that as we go. So digital versus analog. So we say we live in the digital age, right? Digital is only ones and zeros. Analog is, as you can see, it gives you a varied signal. So we work with a lot of ones and zeros. That's what computers actually think in. It's all ones and zeros, yes and no. Okay. Analog sits there and says, okay, here's the data, here's the data, here's the data. And you can literally see it change over time. Does that make sense? So next is position sensors. All right, we have analog position sensors in the potentiometer, or we have a linear variable differential transformer. All right. So if you look at the potentiometer, again, you saw this in intro, but as you turn the dial, it's scooting along this little track right here, and that's what allows you to have the control. Like I said, the other name that I've heard people call this is a variable speed controller. Okay. All right. And then you've got the LVDT, which I believe is using a linear motion with, huh? Yeah, that's kind of what my brain's saying too here. But you have a core, you have a nickel core, and it uses linear motion to determine where it is on this position. It's the easiest way I can say that. But if you remember this, again, this potentiometer, so all it's doing is as it turns, it varies its signal by varying the voltage. So as it varies the voltage, it's actually looking at the output of the circuit as well on this particular one. But its ability to control that voltage is why it can control the speed of other things down the road. Now, encoders. Now, these are actually extremely important because this is what all these robots use to determine the position of their individual joints. Does that make sense? So if we were to look at the big yellow guy over here in the corner, he actually has an encoder we can look at in a minute, but he has two types of encoders. He has the incremental and the absolute. So what is an absolute encoder supposed to be doing? If you notice, this runs in dashes right here. So you've got long, you've got shorter and shorter and shorter. But all this is just to give you positions of where that arm is. It helps precise positioning. Trying to go too fast. So you have precise positioning with the absolute, and it uses the incremental encoder as well. The incremental encoder, I cannot keep tripping over my words here, is more of a digital signal. It's either a yes or a no signal. The incremental one So I don't know how many, if y'all remember the old encoders that used to come in with the cereal boxes. I might just be showing my age on this. Or you might have made it in elementary through high school or something. But an absolute encoder, if you look, this is what the data is looking at right here. Yeah, exactly. It's a lot like a CD disc, because what it's saying is that on each set, it's got a different way of, it's almost like a numerical count. If you kind of understand what I mean with that. So it's saying, well, here, if you start looking at something like binary code, you end up starting off with 0, 1, or 0, 0, 1, 0. That's what this guy's looking at is light, not light, light, light. Then it goes to all the holes are all the holes are filled with different of the color. Oh, I can't talk. But it's the difference between each of these strips that allows it to know its precise positioning. Does that make sense? Thank you. Digital. Mm-hmm.
Binary number, the other one they got the count. So the one on the left has the county control. The one on the right knows where it's at all the time. So you have to set a 0. You have to set a 0. Like on that robot, if you have to set a 0, it gives it and keep a million colors. Mm-hmm. But it appears to be an absolute color because it has counters built into the color itself. So what the controller reads, the controller reads it as if it's an absolute encoder, but in life it's actually. So if you got a device that's got to set, you have to set a 0 on it. So an absolute encoder, we don't have to set a 0 on it. It knows where it's at all the time. Mm-hmm. A binary encoder or an incremental encoder, we have to establish a 0. So by the way, these incremental encoders, these are exactly what's used inside of the robot. You say move so many inches or so many degrees, it's using an incremental encoder. And until the actual application goes down.
Like I said, I'll let y'all see the encoder on the big yellow guy here in just a minute, but it's all done in digital signal. Make sense, guys? Okay. So proximity, there's a lot of different ones. You have one type that's contact, that's a limit switch. Everything else is a proximity set category. Limit switches are taking something physical, turning it into electrical. You have non-contact ones, however, that do just the opposite. They are looking for a different type of physical signal. So not anything that's going to touch it, but something that might like break a beam. I don't know how many of y'all have ever worked with something like a light curtain. You know what those are? So a light curtain is something that's used quite frequently in manufacturing because essentially what you do is you create a doorway and Mission Impossible style, I guess you could say, this thing goes up on both sides of wherever you're trying to get into. If you cross that threshold, it actually acts like a stop so that no machinery is moving and you don't get hurt. Does that make sense? That is non-contact. It's way of breaking the beam.
Yeah. Storage and stuff, and have the gate, and if you try to go the gate,
Mm-hmm. And that's a lot of that's to do with safety too. Mainly because when something's in motion on the floor of a factory, you don't want somebody's hands on it when that happens. You really don't. That might end up hurting. So we got photoelectric. We have magnetic, we have inductive, capacitive, and ultrasonic. Which ultrasonic, we've already played with one of those, right? That's the little two-pronged head thing on your robot. So limit switch refers to the contact device that senses proximity. So if you remember through hydraulics and pneumatics, or if you've been in sensors, this is the one that actually has to make contact. It has several different ways it can do that. You can have the rollerball lever, you can have an actual, almost like a gate that sits there and every time it moves it counts. But it's looking for that physical hit. Does that make sense? Proximity switch are the non-contact ones. So there is a difference in the terms, guys. So keep that in mind. That would actually be a great test question, right? What is the difference between a limit switch and a proximity switch? One is contact, one is not. So there's a huge different gap in between the two. So limit switch operators, you have all sorts of different ways. It only depends upon what you're trying to do. The common ones are the ones that have the roller balls, as you can tell. Others have the wand. It really depends upon the product you're trying to use this with. If it's something big, heavy that could probably snap something, you might go for something a little sturdier, like the roller lever, instead of the long wand that might get bent over time. The thing with limit switches, what do you need to make sure you keep them as? You got to keep them clean, right? That's with any sensor. You periodically have to clean these things. Why? Thank you. If they get dirty, the function drops off. So think about, I don't know if y'all have ever had to work on a lawnmower or anything, or work with one where it starts to gum up and gunk up over time and you have to go in and clean it out periodically. Same with these. Same with any sensor. If you don't periodically clean it, it's not going to live very long. If you clean it periodically and check it and make sure everything's still running right and it's not catching itself, everything tends to run a lot smoother than if you just leave it to get gunked up. And because these have to require a physical input, you definitely don't want these gunked up. Because if it can't make the full contact because it's so gunked up, you're going to end up with one of two problems. One, it won't count. And two, it might actually stall out your production line because it'll stop and back everything up. So, care and maintenance of any and all sensors is probably the biggest, most imperative thing you need. All right, and these are limit switches again. So what is the difference between a limit switch and a prox switch? Yep, what is the big difference? So where do these become contacted? Let me phrase it a different way. Where is my contact on these? You actually have to kind of look for them because they are things like this right here. They're very small. You don't have to have something big, it can be something small. And again, you make sure that you clean it pretty frequently and it will last you a long time. So with non-contacts, one of the things we have are magnetic reed switches. Okay? So these close with the presence of a magnetic field. Why would we maybe want to use something with a magnetic field? Because that might be one of the quickest ways we can get our product down the line. There's several reasons, right? This uses electrical contacts. I lost for words today for some reason. So with the magnetic field, when it comes into contact with that magnetic field and the reed switch closes, then it sends an electrical signal to give the quantity. So it's very cost effective. However, it's an electrical mechanical device, which means that you have to run electricity to it, right? Why can that sometimes be a problem? Because with all electricity, you're limited by the environment you're allowed to put it in. You are always limited by the environment you're having to put something in, and electrical does not always do well.
Yeah, because you don't want to use like electrical lights. I would think
These are the reed switches here. One of the ones they use actually use mercury.
oh no.
Mercury used to be in a lot of things once upon a time. I don't know if your parents have ever told you about them breaking into thermometers and such and playing with mercury. These days we know that's actually very dangerous. We don't do it, but back then mercury was not, considered the danger it is today.
Nah, not until it's testing. Oh wait. Maybe we shouldn't put mercury in stuff.
Mercury is a very interesting element. And
Multimeter.
exactly. The way these work, the contacts have to just pinch themselves together.
So it's got to be perfect. This makes no difference because our current this way, this concentrates the north to this side, the south to that side. If you look, you can literally see it. Right? It's not a contact. So that's why if you keep the power, that's what you're using. You're using a rich switch.
It's years old.
Huh?
It's years old.
Oh yeah, read those plays. If you have time, we'll go over here. Altitude relation. We'll go over and look at the manufacturing line.
Isn't it just like sitting here and you have some magnets?
Yeah, well, what they do is on a cylinder like that. You can't do it with hydraulics. With magnets, it's crazy. You can even use plastic or aluminum. Well, aluminum doesn't compete with magnetic and plastic doesn't compete with magnetic. So the piston on the cylinder actually has a magnet on it. And when the cylinder moves, it goes across that reed switch, and now computer can know whether it's going to be traction. Like I said, down you through, she'll take you on to the manufacturing line, and you'll see all of these lines, see how they're used. We don't have AUT, no research. I know others have these limits. That's why you do something, you have to start this research.
Yeah. So if you're right,
The factor, I don't know if I don't know if it's powerful or not. I actually shutting off the
that would make sense. Closed loop versus
well, the closed loop depends on, ultimately, you tell it to do it, you take the ground it's done. So that would be like a line that I go over and I pull that switch, the light,
yeah.
and I take the ground and what,
Yeah.
and turn on. Closed loop means you tell it what to do, and you check to see if it's done. So if you tell this thing to go 6 inches, then it's got to, you know, motor starts turning, control what we think for the motor, and know the space is going to be one of them. And just have to go 6 inches, right? Hopefully, which one you're going to use depends on what, depends on the application. If you do it open loop, you're going to do it open loop because it's going to be cheaper. You got to know if everything's still in a certain way. It's got to be close. You can have these race switches that are really very cheap. But the problem is that they're still electromechanical devices. Pretty broad. That depend on different components, like the car.
Yeah.
Your vehicle's electromechanical. So these things, after a while, they'll be cheap. We haven't had anything like that. So they have a very good lot there. They're very good. They have a line here now.
One or two.
So this shows you why you have to get it perpendicular.
So we are looking, so these reed switches, like you said, are binary bias, they're either on or off. And whenever they are, the contacts are either open or closed, and it uses a magnet as well as electricity to get the signal that it's looking for.
Same question. Do we have a
Yeah, it's upstairs. I think they just restocked the machines upstairs.
Yeah.
All right, so see there's. So these are some typical magnetic reed switches. And like he was saying, they're an electrical mechanical devices, so they can fail 2 ways. They can fail electrically or they can fail physically. But no, what that's looking for is a magnetic field. What you're talking about is more of a inductive sensor because that's what's looking for ferrous or non-ferrous metal. Hmm? Yeah. Trying not to get too ahead of myself here. So this is using a fluid power cylinder. So if I was to put a proximity sensor on the outside of this, what is it looking for? It's looking for this guy to pass wherever that sensor is so it can trigger it. Make sense? It's looking for that bore. In this case, it's got one that's got a magnet in it, so magnets can sense each other fairly easily, right? So if you put a reed switch with this, it'd be able to find it because of the magnet inside the cylinder. If you're using something like a, never mind, we'll just leave it at that. So then we've got the Hall effect sensor. This is looking for the strength of the magnetic field. It can be digital or analog. So again, what is analog? What does analog look for?
Yeah, digital's ones and zeros, analog down. Good.
Digital is ones and zeros. It's a yes or no. Kind of like these reed switches. They're either in contact or they're not. Okay? Make sense? So then, analog is everything else. Analog is, 0 to infinity and everything in between.
I'll say digital. That sounds like analog.
It is analog.
I guess we got digital.
But you could say the 16, you could say the 15 is the controller that determines you need a trick or what's called a trick.
So, what are some of the other analogs on your robot? What do y'all think?
The sensors.
Not all of
They
them.
did a lot of sensors. I would say the you said, like I said, the light
sensor,
sound sensor,
sound sensor, the motors,
motors, yeah. If you skip that.
the ultrasonic.
I wouldn't count the tones now.
Motors are digital. That's right, I'm sorry.
So
So
typically sound.
motors are actually digital. So the ultrasonic, sound, and the light are all looking for variations. What is one of the biggest digital sensors that y'all have actually used? Which one?
Oh, yeah, it's the last one that says it.
What's this in the back? What kind of sensor is it? What is it? That is,
It says on the back.
that's a limit.
Yep. The sensor, the touch sensor is a limit switch. It's either pressed or it's not pressed. It's thinking in ones and zeros, yeses and nos. Okay. So the Hall effect sensor is looking for a strong magnetic field. So it's a solid state device with no moving parts, but it requires a power source to operate, and electrical operations can always fail, as we all know. And it drops a voltage across simulated contacts. So this one is looking for that magnetic field. Okay? So you've got the sensor here at the top, and it's looking at this magnet as it passes. You've got this notch sensor. You've got several different types. This is a metal detector. So what are these looking for? They're looking for that magnetic field that works with most metals. Does it make sense? Is it there? Is it not? Okay. We got one of these to show them.
You don't think that last week was spring break?
Yeah.
Oh, you're talking about Saturday?
Yeah, last Saturday.
Oh, okay. It's so crazy. I came, I swear I came. There was nobody.
I came back to the river Saturday. I had, I may have showed up like 5 minutes late, but Ms. Bush was here, and we got to waiting around for like,
I ain't see nobody. So I left.
I was Yeah, I ran through all the programs. Now I got a firmware computer now.
Unfortunately, my circuit is over in the other class.
Yeah. So you're gonna have to.
These are the Hall effect sensors.
One of them's latching and one of them's not.
Yeah. Except now we have to do sensors.
Alright guys, so he was able to find some incremental encoders as well as the Hall effect sensor. Those are Hall effect sensors. There's these, which are incremental encoders. So incremental encoders, are they digital or analog? They're digital. Think of ones and zeros. Ones and zeros is digital. Yeses and no's. High and low. So as this would spin, the variation of the light versus the darkness would be allowing it to do the counts and everything else of that. The Hall effect sensor, it's looking again for that magnetic field. I think it has to actually go with a circuit, doesn't it? Putting those with a meter would not work, you have to put it in an actual circuit. Yeah? Yep. Need to work on through this here real quick. So you have to actually build a circuit with this. I don't know how well y'all can see that, but this is where your voltage output is. This is where your voltage input is. And it's looking for that magnet to trigger that sensor. So let's talk about one of the most common sensors, and that's photoelectric light sensor. These detect the presence of an object using a light source and receiver with a normally digital output. Normally digital. That means it's not always digital, it can also be analog. The ones that you are playing with your robot are analog. Why? Because I can set the sensitivity to wherever I want on this. I can make it to where it looks like, oh, is it light or dark? Where is my comparison between the light and dark? These robots have that ability with their light sensors. Yes. A lot of the times with light sensors, especially these photoelectrics, it's looking for things like break the beam. Or how long is the beam, what's the time frame between the time it shoots that beam out and it comes back. So think Mission Impossible, right? And they're always trying to break the beam just enough that they can crawl on through, right? These are those kind of sensors. I don't want to break the beam or else I'm going to get caught, right? Well, most of the time, if we're using these, we want the beam to be broken because that means that something is there and we want it to be detected. Okay? So these are a solid state device with no moving parts. What it means is that it's a sensor that doesn't move. All it's doing is shooting that beam back and forth. It's bouncing that beam of light. So it requires a very clean environment, however. Why? Exactly. You really, really don't want to ever gunk this up. It will not work if you let it gunk up. It pretty much will not work if you let it too much dust build up. Because what this has is almost like a camera. So think about the lens of the camera on your phone. That you might let get fingerprints all over it, if you let it get a bunch of pocket lint in there and stuff like that. What happens to the quality of the picture you can take? It turns bad, right? So with this, same principle. If it gets dirty, it's not going to work. Requires a voltage source to operate, which gives it a point of failure. And it also drops a voltage, which means that it's got its own type of resistance. Some different types, and we're going to talk about them. So one of them is called diffused reflected. In other words, if it's looking for an object, it's looking for the object to bounce the light back to your sensor. Does that make sense? So it's shooting that beam out there all the time up until something comes in front of it and bounces that beam back. That is what it's looking for. You have retroreflective, which is looking for the beam to be broken because it's just sitting there shooting the same beam out to this reflector, and I'll show you all on the line what that looks like. And it's looking for that signal to bounce back. If something gets in front of its bounce back signal, then it sits there and says, hey, there's something here. Does that make sense? And then lastly, you have the through beam. These are very, very common. These are used for things like the light curtains I was mentioning before. It's used for almost like a gate. So you've got a sender on one side and a receiver on the other. And if anything breaks that beam, it sits there and goes, hey, there's something here. Does that make sense? And it's called through beam, however you want to say it. But all it's doing is saying, here is the line, do not cross the line. Okay? So again, with a light curtain, it's got the same setup. Senders and receivers, and you've got lines of these invisible light shines that you're trying to make sure it doesn't get caught up. Does that make sense? So here's some different through the beams. So you have your sender on one side, the receiver on the other. Okay? Now, let me ask you this. Do you think you can actually see the lights that are going by? No, this is not Mission Impossible where you grab a little dust or you grab some hairspray and you sit there and go, shh, and all of a sudden everything just shows up. No, that doesn't really happen in real life. Unfortunately, unless somebody is using like a laser pointer. And even then, if you've ever looked at a laser pointer, you cannot see the light coming from your laser to where it hits the wall. No, you see where it hits the wall, right? So that's the same thing for through the beam. It's not something that's visible. Yeah, I always find it funny when in spy movies they just sit there and go, hey, I've got this can of hairspray. Let's see if we can.
Like on the movies and stuff, the spy movies and stuff, they be flipping all through them. So those are different because like you can actually see them.
Because it's Hollywood, and they're actually using things like string and stuff to sit there and do that. Because if you really think about it, light does not become visible under any circumstance whenever it's just transmitting. Only when it hits something. Well, the whole thing is, how many of y'all have a garage door? Okay, and that garage door, if you look down on both sides of the garage door, what's happening? You have the two sensors. If I remember right, they're through the beam sensors.
If it's going up or if it's going down, and the sensors are blocking the way, it's not open.
Exactly. Well, the whole point of it is something like if you have a pet that decides they want to run through the garage door, they're not going to get caught. So with a through the beam, that's exactly what that is, by the way, guys. That is generally a through the beam. And what is the problem with having something like that is if you knock one sensor out of place, what do you have to turn around and do? You got to find a way to line them back up. Because if one of them's knocked out of place, or even just knocked out of alignment just a little bit, it sits there and constantly sends that signal back to the garage door opener saying, hey, there's something interfering with my signal.
Yeah, like that game, this thing is retroflective. It's got a sensor, it's got the little reflector on the side.
Mhm.
If it rains and stuff, it gets inside that reflector, it'll throw that beam and everything.
Exactly. So light sensors are extremely sensitive.
Yeah, I hardly know half the time because it has a sensor to tell, oh, is it dark outside or is it not? And it changes the interior, like displays and everything. Well, it thinks, oh, it's dark. Well, guess what? We're going to turn everything in the car dark then. I'm like, what? No help.
All right. Focus. Keep the focus, guys. Keep the collective ADD under control. So through the beam, again, it's just looking for something to break that beam. So, if you happen to end up standing right in front of the sensor, the garage door can't come down on you. With a retroreflective. Okay. All right, I'll see if I can't get us another flash drive.
I gotta go.
Yes, sir.
Like one down.
Okay. So retroreflective sensors. So these are looking for reflected light. It's trying to bounce that beam back from some form of a target out there. Okay? And as it bounces that beam back and forth between it, it looks for something that'll break the beam. Then you have your diffused, which means that it's just sending that light out and it's looking for something to eventually reflect it back and say, hey, something's here. Yes. Glass is prismatic. So what does that mean? It means that it's going to reflect light back in a different way. So. All right, so we have optical interrupt switches. Okay. So again, these are a phototransistor type. They're looking for some sort of stimulation. So next thing that you'll find fairly common besides light sensors are these. And these are capacitive and inductive prox sensors. Okay? Before we go further, guys. All right, so capacitive and inductive proximity sensors. These are solid state limit switches that have no moving parts. We like not having moving parts. Why? Less wear and tear. What else? Less likely to go wrong. What else? Cheaper to maintain. That's one of the biggest ones. Anybody else? Why do we not like having sensors that do not have to make physical contact with anything or have any moving parts? Efficiency, and what were you saying? Maintenance is a lot easier. Essentially, the more moving parts you have, the more likely you have something that will go wrong. The more complicated it is, the more likely it's going to break. For example, if you look at, I think the biggest example that I can think of these days is the new tailgates on the truck that have like 6 different positions. The whole thing is that eventually all those moving parts are going to end up broken, corroded, or something, and you'll have to replace it, and it's going to be very expensive to replace it. More moving parts means more points of failure.
I don't want the tailgate to go this way. My roof is sit on a normal tailgate. You're going.
So, no physical contact with the item being sensed is the great thing about this. This actually can be operated in dirty environments because it's not looking for anything. It's just sending out a magnetic field to try and figure out if there's something there. Capacitive can be used for solids, liquids, and gases. Inductive is for metals. Does that make sense?
You know how on the new trucks you do have to tailgate simply on the either on the GT or it's on the Chevy. They have it to where you can plug up, like they have outlets in the back of the truck now. I'm over here saying like, how much is that going to do? I'm like, how much battery are you going to drain off your off the actual engine battery? Yeah, I'm like, how? Eventually, your battery's just going to die unless you have the off. Okay, I'm getting a truck because more than likely I'm using the balls up and work on stuff. I'm not going to be sitting there hooking up a TV or something to the back of my vehicle. No, because like you already have an issue if you leave your car off for a certain amount of time. Eventually, that battery's going to die. I can imagine having like a 50-inch flat screen TV hooked to the back of the drain faster. Or better yet, you know.
Okay. Let's focus. So capacitive proximity switch sensors, they use two metal plates separated by a dielectric. It's determined by the physical characteristics. So capacitive sensors can be used to sense anything that will change the dielectric constant of the insulator. So that is solids, liquids, or gases. So these guys can detect just about anything, depending upon how you've got it set up. Does it make sense? Propane?
No, it's really bad gas if you can't smell it.
Carbon dioxide?
Yes, like carbon dioxide.
Yes. Carbon dioxide and carbon monoxide testers. It does. I'm trying to remember what kind of sensor it is. They use infrared mostly. And for carbon monoxide, these electrochemical sensors. Yeah, they use infrared on the carbon dioxide. All right, so induction. So this an electrical conductor looped into many coils. It's determined by physical characteristics, including the number and proximity of the loops and what it's coiled around. The amount of opposition to electrical current is in the formula current on screen, just 2 pi frequency and the amount of inductance. Inductive sensors are looking for anything made of ferrous metals. Y'all know what ferrous metals are, right? Huh? Things like iron, cobalt, nickel, and copper, and things that are magnetic is what you're looking at with this. There's several different ones out there. The most common you'll run across is iron and nickel. Mhm. Silver, gold, and platinum are actually non-magnetic, and that's why they won't detect certain types of jewelry. But if the jewelry is plated, then it will detect it because the under coating of the plating is generally made of bronze, which is a mix of copper and tin, or it's a mix of pewter, which is, if I remember right, little bits of steel and tin, basically crap metal. So we have distance sensors. For those, we use what's the ultrasonic, which, as we've talked about before, ultrasonic is just like echolocation in animals, right? What it's doing is it's sending out a signal and it's listening for the bounce back. Kind of like when you go into a very big room and you just can't resist but going, echo! You're listening for it to come back. You're listening for the sound waves to bounce back. Same thing with ultrasonic, is it's using sound waves, high frequency sound waves, and sitting there and going, echo, and listening for it to return. If it returns quickly, it knows that there's something at a close distance. If it does not return at all, it knows that there's nothing in front of it. So if you've ever seen things like dolphins, the way dolphins catch their prey is they use echolocation. They click and they listen for anything that reverberates back. And it's how that they can find animals that are even hidden under sand. If a fish or a stingray or something like that is hidden under sand, they can actually still see it because the density of the sand versus the density of the animal clicks back at a different rate. Or you have things like bats. And the whole reason bats hardly ever fly into anything, especially something like glass, is because they are using clicks and squeaks to send out wave signals, and they're listening for the bounce back. So they don't run into glass, believe it or not. They're not like birds. Birds have a hard time seeing glass. Bats can see it clearly.
We have a room that's got like several panes of glass, and we'd be sitting there watching a movie or whatever, and you hear, oh, and you look over, and there'd be a bird just in a daze looking around, and like, oh, I don't have to myself something. There was this one mockingbird that did it 4 times in a row. Got up, did it again. Got up, did it again. Got up, did it again. Did that for several weeks. Until I think it finally died of the These are what we assume.
So with ultrasonic sensors, they work a lot like the animal kingdom's echolocation. You have photoelectric, which we've talked about. It uses light or time. It can do it in a triangulation or a time of flight. Talk about that here in a minute. So distance is the measuring of the amount of space between two things versus level is the amount of vertical distance. That makes kind of sense, right? Distance, if we're talking distance, how far is it from here to my car? That's distance. What is the level between here and the ceiling? That's talking about, of course, how far up is the ceiling in here. Does that make sense? Ultrasonic sensors. These convert ultrasonic waves into electrical signals and vice versa. So you have a transceiver, or it's done through transceiver. So you have one side that's the transmitter and one side that's the receiver. So again, this goes back to the echolocation. You have the animal that's squeaking with either, there's a couple of different organs they use for dolphins and whales. They actually have fluid filled in their head and such that they are emitting it through there, and they are listening for that bounce back. In something like a bat, they're actually emitting it from their mouth, and their ears are trying to catch the sound back. And these guys are digital or analog. So if they're digital, they're just looking for any signal back. If they're analog, they're looking for a certain level of signal back. So with the ones on your robots, are those digital or analog? The ones on your robot are analog because you can set whatever level they're looking for back. Pretty much, yes. With digital, you're looking essentially like at the touch button on the robot. Is it pressed or not pressed? Yes or no? It's like the old thing of Yoda, do or do not, there is no try. Same thing for these. For digital, it's either yes or no, there is no middle ground. Okay? With analog, you have yes, no, and everything gray in between. Does that make sense? So these particular sensors can be used for distance sensing. They can be used for movement. So think about the sensors that detect your movement out in the yard, right? Those could very well be ultrasonic, or they could just be simple motion detection, which I think actually uses ultrasonic, so I might be wrong. Levels of solids and liquids, fairly easily can detect that. Speed and direction. In other words, this is what the cups can use to see how you are speeding. There's two different ways that they can detect that. But it is limited by the surface shape and density. So if there's something that's not dense enough for it to pick it up, it won't. Generally not one of the bigger problems with ultrasonic, but it can be every now and again. One of the things you have to watch out for with ultrasonic, though, is if the level is weird, then it will not pick up what it needs to pick up. Does that make sense? All right. So like I said, it's just like echolocation. By the way, if you don't know what the one down here is, that would be an ultrasound, which uses... Well, it's not just for that. Ultrasounds are actually used as a medical detection device. So they can actually ultrasound something like your lungs or your heart, your stomach, your everything, just to see if there's something that needs to be worried about. Well, most of the time, a baby's heart, when it's not born yet, is very, very fast. But at the same time, it's still something that's developing. And that's something you got to kind of keep in mind, is that anytime you're listening to anything inside of a baby before it's born, is it's still under development. So it's kind of like a cupcake in an oven. It doesn't look like a cupcake when you put it in. It's just a bunch of dough. And no matter what stage you look at it, whenever you're looking into the oven, it's still a bunch of dough up until you take it out and it's done. So it's still, it has to go through the process. So again, it's all about reflected signals with ultrasonic. Photoelectric we've kind of talked about. You have two different ways that photoelectric works. You have triangulation. So this means that the signal is transmitted at an angle and it's looking for that same angle of reflected light. And then you have time of flight, and that measures how long it takes for the pulse to get back to it. So triangulation, it's literally sending out this signal and it's looking for where is it coming back from. And it's able to calculate distance that way. And then you've got time of flight sensors, which is how long does it take for my signal to go out and bounce back. Does that make sense? Ultrasonic level detectors are pretty frequently used. So we use discrete level detectors or continuous. One of the most common sensors, how many of you have ever actually looked into the back of your toilet? Into the tank? How do we have, yeah. Open up the back of the tank and move to the side so you can actually do anything in there. So the float switch is actually one of the most commonly used switch types with liquid level. Why? Because it is very, very simple tech. Pretty much. A lot of people tend to still use the float switch because it's very, very simple tech. All you have is this ball filled with air, and as the liquid level goes up, it raises the ball up. Generally, that's also attached to a limit switch of some type that is going to either cut off the water level rising, like it does in your toilet, or it will trigger something else to happen. So maybe it's trying to trigger the water to just move out. Looking for the level, then it just pushes it all out the other end. So these are probably the most common ones that are out there. What, a float switch? It's not.
If you knew how to fix and operate this stuff, you wouldn't have to pay somebody to do it, right?
Considering that I have helped change out the insides of a toilet before, yeah, it's not that hard.
So I would agree that most people don't know how to do it.
Well, let's put it this way. You want to. One of the things I've actually had to do is in order to fix where you know where the S hook is between the chain and lever, I've actually had to replace that once at work with a paper clip. It worked too.
I mean, there are certain things that you can fix like small objects, like with the German ingenuity, like let's say like the water heater gate, right? Well, what some people do is, especially like you'll see these things like in the police. Well, if the spring is bad in that cycle, what they'll do is they'll take a pin, unscrew that, take the spring out of it, and put it in. Same principle.
So then we also have photo sensors that can be used to detect level. If only because whenever it gets to a certain level, it'll break the beam. You also have things like resistance probes. So as the water level rises, this is going to send out an electrical signal. The float and weight. So as the float moves up, the weight will move down. You have pressure sensors that can be used, load sensors, electrodes, or ultrasonic. 9 times out of 10, you're probably going to use a float switch just because it's cheap, simple technology. However, if you have to have X amount of precision, you might use something else. If you have to have a certain amount of weight to it, you'd probably use either a pressure sensor or a bunch of load sensors. Does that make sense? So pressure. So a pressure switch is trying to detect pressure against itself. Now this picture is not the greatest, guys. But it's looking for a set amount of force to activate the contacts once that is reached. Okay. Pressure switches use different sensing devices to detect the amount of pressure. It always depends on what application you're trying to use it for. Does that make sense? RFID, these use electromagnetic or electrostatic coupling in the radio frequency spectrum to automatically identify the tags attached to an object. So think about how many of y'all actually go to the mall to shop? Or you go to someplace and try and get electronics. Generally, they have one of two things. They either have a big tag stuck to it so that you literally, if you leave the store with it, you're not getting it out of the package without destroying the product inside. Or B, they've got the little white tag that's about a little square tag like that. That's got all the swirls and stuff in it. Those are RFID tags. What those are meant to do is if you try and pass through the sensor with that thing still active, it'll detect it. Yes, because if you don't deactivate it, you get the the alarm has been triggered. Please wait till a store associate comes and gives you a hand. I'm paraphrasing, and that's only because I've worked retail so long. It's a very frequently used thing with retail because y'all would not imagine just how much product tends to somehow get up and walk off. It happens with a lot of frequency. There's a reason we make it hard as FRUD to get the tag off, and that's because too much of it wanders off otherwise. Yes, and that's kind of the whole point, is that if you get it off, you'll damage it, and it just isn't worth it. How many of y'all remember Goodies, when that used to be where Second and Charles is in Hoover? Okay, so when you go into Second and Charles and you go up to the checkout counter, have you seen the little gray circle things that they've had behind the plastic glass there at the register? Those are the old Goodies tags, left over from longer than you probably understand. Those were the RFID tags. So if you tried to walk out the store with one of those still attached to the clothing you're trying to take, you're not going to get it off because it had a circle pin with a pin through it that went out into that big circle disc. And so basically you had no room between where that pin was and where the circle started. So if you were going to try and get that off, you had to have the right mechanism to pull it off with. So the passive tags, the little sticky tags, are powered through induction provided by the frequency supplied by the reader. Active tags have a local power source operated at a greater distance from the reader. So this is the difference between an active and a passive tag. So a passive tag is what you generally find on clothing, in books, You all know what I mean. Those little passive tags that are attached to everything so that you can't just randomly walk out of the store with a product, right? Some of them have ink in them. That way if you, well, I mean, if you bust it, the ink comes out. Those are the worst ones. Yep. The other way is you have the ones with the pin through it. The only way you're getting that off is if you tear up the clothes, because generally the pin is stuck really deep in there, and you're not going to get a pair of plier cutters in there. No, you have to have something like lead or something. Really? Mm.
My store doesn't have tags, but they always sell food products. So, I mean, if you're that bad, you got to steal food, and
So active tags have a local power source. You might not have seen these as often. They're on the really expensive pieces. The really, really expensive ones have personal RFID tags that make it to where if you try and run off with them, they're still sending out a signal. And then lastly, we have temperature. You have things like thermistors. These are externally powered and varies with temperature resistance. You have a negative temp or positive temperature coefficient, which means that the resistance will decrease as temperature rises, or it'll increase as temperature rises. Trying to remember exactly what the top so thermistors typically will be able to read up to trying to think about so these guys can run a very big gambit of temperatures. And then you have things that are like thermocouples. These produce a voltage proportional to temperature. Does not need an external power source. It uses a junction of dissimilar metals. It determines the temperature range. It can measure between 0 and 4,200 degrees. So thermocouples are, do y'all know what I mean when I say a kiln? A kiln, K-I-L-N. No. Think back to art class. Art class. Pottery kiln. You have glass kilns. You have all sorts of things. What these essentially do, they do one of two things. If it's something along the lines of a pottery kiln, what you're trying to do is pull all the moisture out of whatever object you have placed inside the kiln. You're trying to bake all the moisture out of it, basically. If you are trying to melt something, you can use a kiln to melt metals, or you can even melt glass. Yes, but this has the ability to stay at a steady temperature. And the thing about this is, so I don't know if you've ever watched How It's Made. There's one where they're talking about how glass bottles are made for producing soda. And the thing is, they use almost like a conveyor belt full of melted glass. So whenever they're ready, they just move it down, it deposits the glass. But the thing is, you can't ever let the glass go cold. If you do, your kiln is toast. Your furnace is toast. So these are used to maintain and check the temperature of these devices so that you don't end up with cold glass, which can't really be remelted very easily, especially since you're going to have to chip it all out of the furnace. That's a fun job, isn't it? So you have to be able to maintain the temperature. And then you have resistive temperature devices. These uses a metal device to measure temperature, and it can replace thermocouples at temperatures less than 600 degrees. So over 600 degrees, this thing don't work no more. Okay. At over 600 degrees, it don't work very well. And then infrared. How many of y'all know what infrared is and what it does? It measures light and the wavelength of light to calculate a temperature. So if you've ever seen a thermal camera, that's infrared. Okay. Actually, no. Infrared has become very big on the market. They actually use one of the biggest uses is in the power companies. They actually can use infrared to look at the power lines and at the transformers and things like that to see if they're working right. They've actually made quite a big thing in the private sector. It's one of the ways that they use to look for, humans or animals that are on the ground if you're trying to find them without spooking them. Because it picks up on the body heat as a wavelength and it's able to translate that. Not that big because it's actually quite still expensive. But one of the things, the downfalls of this can be if I had an infrared camera on me and I decided to come up here and put my hand on here for about a minute or so and then take it away, my handprint will still glow under infrared. It's kind of cool. Any questions on that, guys?